In the last segment, my cell phone was ringing, and not that I ended it because of my cell phone, but we were at about 10 minutes, but actually it just turned out to be a telemarketer, so sorry about that. Segment 3, we're going to keep working on trying to figure out if we can hydrogen bond molecules of the same substance when we go from a gas phase to a liquid phase. And we saw that water would do it. We saw that this carbon compound would do it because we have a partial positive hydrogen and a partial negative neighbor. Partial positive hydrogen, partial negative neighbor. And we can see that we can hydrogen bond in multiple places. Okay, CH4, our Lewis structure, will look like this. CH4 will bring another one into the vicinity. So our CH4 has no polarity, okay? The carbon-hydrogen bond is not polar, okay? If it is not polar, then what that means is that this CH4 and this CH4 have no interest in each other, none whatsoever. They will not attract. In fact, they'll just separate. And so this will tend to want to be a gas at room temperature because there's nothing holding these two together. Okay? NH3, our Lewis structure is going to look like this. And again, if you don't remember how to make your simple Lewis structures, you're going to want to go back to Unit 2 or wherever it was that you learned how to do that. Okay? You need a lone pair. So our shape here is pyramidal. So I should probably make that more obvious on the next one. Okay, so we're going to make a pyramid. Okay? Then we're going to look at our electronegativity chart. And we're going to see nitrogen is 3.0, hydrogen is 2.1. So when we subtract those, the absolute value difference, whether this minus this or this minus this, is 0.9. That means the nitrogen-hydrogen bond is polar. So, because nitrogen has the higher number, nitrogen is partially negative, hydrogen is partially positive. Partial negative, positive, positive, positive. And so when we bring these into a proximity of each other where they're close enough to be a liquid, okay, so do whatever works. I just have little stickers at my house. If you have pennies or little circles or little dots or something else you could use as a visual aid, then feel free, okay? Are these going to stick together or are they going to separate? Well, I have many places here where I can hydrogen bond. I have this partial positive hydrogen and this partial negative neighbor. So those are going to attract. I can also have this partial positive hydrogen, perhaps, and that partial negative neighbor. Okay? So these are going to want to attract, and the things that hydrogen bond are more likely to be liquids at room temperature. So water is more likely to be a liquid at room temperature. This carbon compound is more likely to be a liquid at room temperature. This one is more likely to be a liquid at room temperature, and so forth. Okay? Now, again, since water is the most important in a class like this and with biological sciences, we're going to stick with water as our solvent. And again, these are called aqueous. Okay, so now what we want to do is say, okay, what happens if I want to take one of these molecules, for example, and instead of mixing it with another of its kind to put that in liquid form, what if I want to take one of these and put it in water to make an aqueous solution? Okay? So for lack of better demonstration, I want to take one of those, I want to put it in water. Is it going to mix? Okay? Now at its simplest, that is called like dissolves like. And really what this is how things dissolve or dissolution at the molecular level. Okay? Now we already saw on page 1, okay, we already saw on page 1 that I could write this like this, that when I take a solid and I put it in water and get it to dissolve, that I end up with these aqueous ions in solution. I just can't see them. Well, how could we draw this on paper? Well, again, we know that sodium chloride or table salt, if we take some crystals of it, that our solubility table and just what we know about sodium chloride is that all sodium compounds will dissolve, and therefore it'll be aqueous. Well, what that means from page 1 is that we have sodium ion surrounded by water and chloride ion surrounded by water. So let's look at that more closely. There's our sodium. There's our chlorine ion. Okay? Now our water, we know, is polar. Partial negative, partial positive, partial positive. We know that. And if you don't know that, you need to commit that to memory very, very quickly. So the question is, how is this water going to be oriented around the sodium so that the charges do what we want them to do? Is the hydrogen going to be attracted, or is the oxygen going to be attracted? Well, clearly it's going to be the oxygen, because the oxygen is partially negative. Oxygen, partially negative. Oxygen, partially negative, and so forth. And I'm just, well, here, I'll put the pluses in here, okay? Okay? So what we see then is a whole bunch of water. We don't see the sodium. Over here, what part of the water is going to attract to the chloride? Well, it's going to be the hydrogen part, because that's positive and the oxygen is negative. Positive, negative, positive. So we don't see the chloride, the water just surrounds it. And also, as a semi-tangential aside, the water still attracts to other waters. So what we can say is, will the sodium chloride and the water mix? Well, we know that. We know that intuitively. We've done it a million times. What I could say here is that the solvent is charged. There's charge. And there's charge on the solute. Okay? So what we're going to be looking for as we are developing this is we are going to be looking for charge on the solute, charge on the solvent, and if we have them both, we will assume they will mix. If we don't, we will assume they're not going to mix. In the next segment, we will keep working on this.